All right, so for our first demo, I have got, this. This is a file that is going to load, scroll up, damn it, 2 sound files, okay? One of which is, again, a random Chemical Brothers song I grabbed, because it happened to be the only audio data I could get in waveform quickly. And then the other one is going to be a somewhat unique friend of mine reading a very bad fanfic for his own entertainment. And what I'm essentially going to do is try to train the network to tell snippets of each of these files apart. So what I'm basically trying to do is get it to tell the difference between techno and human voice, right? Which intuitively we would think would be an achievable problem, right? So again, this is actually pretty easy. Like getting the NumPy data out part is very easy, right? Because sf.read just gives us a NumPy array. In the case of the Chemical Brothers song, we're going to get a arbitrarily large number by 2 NumPy array because the song is stereo. And in the case of this interesting thing, we're going to get we're going to get an arbitrarily large 1D array because it's mono, right? And kind of like I did before, I left some more sophisticated stuff down at the bottom of this file than I meant to. All right, so as we did before, I've decided not to edit the file. I'm lazy. As we did before, just comment all of this out. And let us see what we get with our initial import, okay? So we get a big array of 2 samples, right? 2 column, right? So, because it's stereo, right? Left channel, right channel. And if you look at the shape of that thing, we see, again, big number. So it is 12,436,189 samples, 2 apiece, because it's stereo, right? And if we look at the sample rate, which I stored in Kim's sample rate, we see that it's 44.1 kilohertz, right? So if it's 44.1 samples per second and that many samples, we can do, just as a sanity check, some fairly simple math. If I could type. To find out that it's about 281 seconds long. You just heard my cat sneeze. Which is about 4 minutes, 4.70 minutes. Which, that seems like the length of a track, right? That makes sense. And if we look at the voice track, it is a 1-dimensional array because it's mono. Of length. Ooh, come on. Come on, mouse. What is going on? That's what's going on. Of much greater length, right? 153 million samples. And if we divide that by the sample rate, let's see how long that is. What did I mistype? Tuple? Oh, right. Need to get the first item out of the tuple. There we go. 58 minutes. Why is it 58 minutes? Because it's a guy reading text. It's much longer than a song. Let us compare for a moment the sample rate. And I have forgotten what this number is going to be, right? So that one's 4,400. What is the text sample rate? Okay, good. So those need to match, right? Because the same signal will have a completely different representation if the sample rates are different, right? If those don't match, if the sample rates are different, then we're comparing apples to oranges if we examine them at the sample level, and our neural network can potentially learn to do really well without learning anything about what the properties of human speech are, because the sample rates are going to be entirely different, right? It'll just be seeing different kinds of data. Okay. So what is this thing? This, if you haven't seen it, because I have a yield statement in here. There it is. This is a convenient generator that I wrote to break our big, long sound file into little sample windows, right? So we can't just feed a 150 million sample sound file into a network, right? Networks are stateless. So we actually will learn later about a time-aware network that you kind of could do that with, but that's not this, right? We need to break our big, long file into little windows that we can feed, right? So if this is our big, long mono file, then we need to come through here and break it into little windows, right? That we can feed to our network. And I'm drawing it this way because I decided to make the windows overlap. Why? No especially good reason, other than that I wanted to have the network see every sort of, basically every byte twice. Right? And so this convenient iterator does that. You give it a window width and a channel to break down, and optionally a stride. Stride is how far it goes each time. And optionally a limit. And what it will do is output, there we go, up to, why is that a plus? What did I do? Oh no! Oh no, what? Alright. Whew. Alright, and what it will do is output up to limit of those sample windows, right? So the first thing that it does is if stride is none, if I didn't tell it what the stride is supposed to be, it assumes, that I want to advance by half my window width every time, right? And that results in that sort of even thing that I was doing before, right? Where every sample, I guess except these, is covered by two of these windows, right? So it keeps an I, which is our current index, in the channel. And while we have enough data left to make a sample, right? So it checks and makes sure that I plus window is still inside the length of the channel. And while it is, it snips out that little segment and it increments the current position, right? So we have to do a little bit of careful data preparation here. A sample of silence from a techno song is very much the same as a sample of silence from human speech, right? Because they're both silent. Neither has signal in it. So since those don't help us tell Chemical Brothers from human speech, and in fact, since we can't tell, right, techno silence from spoken silence, we have to remove them. There are much smarter ways that I could do that. All I do right here is check to see what the maximum inside of the sample is. If it is over 0.2, and again, remember that pysoundfile very politely normalizes these to the range 0 to 1, right? So if it's over the fairly low, if the highest point in the sample is over the fairly low threshold of 0.2, we're going to keep it. If it is below 0.2, we skip it. If we decided not to skip it, we yield it, Then we see if we were over our limit, or then we see if we're tracking a limit, and if we are tracking a limit, we're going to increment our count of produced samples and see if we're over the limit, and if we are, we give up. Okay? So why do I care enough to track the limit? Because one of these sequences, right? So the techno song is a certain length, and it's 2 sample, right? But then the spoken word track is much longer. And we've already said that if our classes are unbalanced, we would expect our network to learn poorly. So I want the ability to chop these at the same length so we have the same number of samples, right? And I hope you all have seen a generator before. I really do, right? A lot of y'all have written some fairly sophisticated Python code, so I'm kind of expecting that. But I could be about to be wrong. And I'm hoping I don't need to explain what that yield statement does. All right, so what I do is now I just call it, right? So I've defined my generator. That makes calling it very easy right here, right? This is my generator. This is going to return a generator object. This list will just convert that to a list, right? So we don't have to, this is like an easy, not having to think about it way to just take a generator and here, give me a list of the stuff in the generator, right? And then I'm going to pack that into a NumPy array, right? So notice the numbers I picked. I picked a window width of 100. So there's 100 samples per window, right? And notice that my code isn't smart enough to handle stereo audio, so I just decided to pick the 0th channel, right? This is 0 for I think left and 1 for I think right. And I just decided to pick one of those, right? This colon means all of, right? So all of this index, the 0 for this index. So it's just the one row, right? I picked a stride of 50, but since that's half of 100, I could have just left this blank. And I just picked a fairly low limit, right? I decided to get 5,000 samples. So how many is that? Well, if our sample rate is 44 kilohertz, or 44100 samples per second, that's about 1/10 of a second. And then I did the same for the spoken word, right? Same numbers. And same procedure. Get an iterator, get a list, get a NumPy array. Oh, right, yeah. So, then I produce, sorry. So that's 2 different NumPy arrays. So to feed that in as the x's, I need to stick them together. Fortunately, NumPy has an easy function to do that, and that's np.concatenate, right? So np.concatenate is going to take all of these contained arrays and just stick them together as long as the sizes match, right? So they need to be the same in all dimensions except the first, right? Otherwise, they won't be able to be stuck together, right? So it needs to be, so for example, right, they are both some number times 100, right? Where that number is in fact 5,000, but let's pretend it could be different, right? By 100, right? It can stick together a j and k by 100 list or array into one really big k plus j by 100. So that's what's happening, right? It's just sticking them together. So these could be potentially large in memory. They're actually not, right? But if you were processing a lot of audio, the total size would get to be very large. And so I'm going to come down here and delete my original samples after I produce my inputs, right? So del will delete these arrays and cause the garbage collector, hopefully at some point quick, to get rid of those. So I say hopefully at some point quick because I don't think the garbage collector is guaranteed to run. Like, I don't think it has any run guarantee, right? but we're just kind of hoping that when I call del, the garbage collector will grab that memory and free it. And again, I don't need the original Kim's samples once my input exists, right? Because the inputs array contains both of these. So the next thing I'm going to do, and this is a trick that, the next thing I'm going to do is I'm going to use, now I need my labels. Okay, now I need my labels. I can create one array of labels by using np.repeat. What I do with that is just give it one row, and it will repeat that into a big, to a bunch of rows, right? So if I want to give it like my one row, it will expand that into as many as I ask it to, right? Then, well, okay, so I need as many sort of Chemical Bros labels as I have Chemical Bros samples. So I first specify what my label I want it to be for Chem Bros. Then I tell it to repeat that as many times as I had Chemical Brothers samples, and then I have to tell it which axis I want it to repeat on, right? Because I want to tell it that I want it to do like this and not this. See? So I have to specify which axis I want it to be repeating along. Instead of, so this code is egregiously condensed. Instead of storing that anywhere permanently, instead of assigning it to a variable, I just immediately do that and then do it again with a different label for my spoken word, and then I just pass both of those into concatenate and assign that to labels. See? So again, that's very, very dense. What I'm doing is I'm taking the label I want for my Chemical Bros, I'm repeating it however many times as I got Chemical Bros samples. I'm taking my label for my spoken word, I'm repeating it however many times I got spoken word, and then I'm taking those two big 2D arrays of labels and I'm sticking them together with concatenate, and I'm storing that in labels, okay? Finally, I have my network down here, and I was fiddling with it a little bit just to amuse myself to see if I could get the loss to be better, because spoilers, it's not going to be good. But this is or can very rapidly be, and we don't need any random noise, right? This is or can very rapidly be a very simple version of the network we had before, right? Notice already that this is much similar to, but much smaller than the network we were using to process MNIST, right? We only have 100 inputs, so we don't need that many neurons or units per layer, right? And if we run this, notice that it's going pretty quickly, right? Because it's not a very large network. Notice, however, that the loss is not good. So while the training loss, move this, while these training losses, right, which are these numbers right over here, are consistently going down, our value loss is kind of oscillating quite a bit, right? We see that it hits 1, it hits 0.9, it hits 0.8, it hits 0.9. It's not getting very small, right? I can think of at least one reason that it's not going to, and I already said it. So pause the video. Can you think of a reason why that loss is not going to get very small? It is because of the sample size, I think, right? So one of many potential reasons is the sample size, right? 50,000 sounds, 5,000 sounds like a lot of samples, until you realize that's about 1/10 of a second of audio, right? Another question, or another problem might be, is that these windows might be too narrow. Again, 100 inputs sounds like it might be a lot of inputs until you realize that that is 100 over 44100 of a second, right? Every one of these windows is going to end up representing, oh, I'm going to be stupid because I can't do the most trivial math in my head, right? 1/441th of a second. That's not a lot, right? And if you have a sample at 200 hertz, right, that is too little to capture that signal, right? And a lot of, I think, the harmonics of the human voice might be in this range, right? Certainly, if you're talking about electronica, which has a lot of low-frequency samples in it, you might need a much wider window to adequately capture those sounds, right? So what might help? Making this number bigger and making this number a lot bigger and then making these layers a lot bigger, right? Let us try that. So yeah, notice while I've been talking that the loss has become catastrophically bad, right? So the value loss has gotten worse than where it started, right? Even though the training loss is becoming pretty good. So what we're learning is that the network is just memorizing the inputs that it's seeing, right? It's not actually learning a useful rule over what separates the sound of techno from the sound of talking. Let's way ratchet that window width up. I actually don't know if we're going to have enough. Well, yeah, we probably will. And let's make this a 10, shan't we? And let's find out how many samples we end up getting. So again, I'm going to just comment everything out, run it, and notice that it's taking significantly longer now to build that data set. I hope I didn't mess up. This is my dear friend htop. It is going to tell us what our memory usage looks like. And I noticed that our memory usage is not insubstantial at about 10.4 gigs. So another lesson here, right? These data sets can get large very quickly, very surprisingly, right? So I added a 0 here and I doubled here. Our memory ended up getting substantial. Let's del those samples that we don't need anymore. See how that helps our memory, shan't we? Not yet. So I guess either those were not very large or the garbage collector hasn't hit yet. So we're still looking at 9 gigabytes of used memory. Okay. Or my guess about what the sizes of that is might be wrong. It's possible. I've been wrong before. Okay, so now let us uncomment that. Let us make a new console so that it clears out some of that old memory. Let us run our script again. So when I made a new console, we went down to 5 gig. So now as our code runs, we're seeing it go up to 6.5. This is the fun part. And I think this is sort of, yeah, this is the fun part. This is useful learning. Whoops. Oh, and I forgot to change my network topology. I am so dumb. All right, so let's just, you know, we're probably going to need at least one more layer or two. So let's change our network topology to match, shan't we? There we go. Let's make that a little bit smaller, more aggressively, because we don't want to be here all night. But yeah, this is sort of the fun part of this process. I think this is worth going through because this is probably a lot of what you're going to end up doing on your project. And these are some of the issues you're going to encounter on your project, right? You're going to use a setup that seems like a reasonable starting place, and it's going to take a little bit of thought to go, oh, it's because my window is 1/441th of a second is probably part of why it's not working, right? And then you're going to try to build better data, and you're going to blow your memory up. You're going to go, oh, if I just naively build better data and put all of it in memory, it's going to be like 15 gigabytes. Whoops. And you get to kind of fiddle with these things, right? You get to sort of try stuff, find out, oh, it didn't work, and then you get to have learning experiences as you see if you can find a way to make it work, right? And looking at our results, we'll see if that continues, right? Because 3 could be a fluke. All right, it's going up a little bit. But if we look and we see that we are maxing the CPU usage, hopefully the record is continuing to work well. It's going to be real fun when I find out it failed every time we train something. Okay, so the loss went down. It's going up. We'll see which way it continues to go, right? Because again, like, we already know there can be noise in the validation loss signal, right? It is not doing what it did before, where it's going up rapidly and bouncing back and forth very badly between epochs. So the validation is now doing better. I'm going to hold off on calling this problem solvable. Intuitively, we expect that this would be a very solvable problem because we expect that speech and techno sound real different, right? So if we well represent our data, the network should have plenty, to pick up on and make this distinction, right? And now that we've given it a bunch more weights and a bunch wider sample that's enough for it to get like whole sounds, right? Enough to tell kind of like a grungy, nice EDM sound from the sound of a person talking, we would expect it to do a fairly decent job of learning this rule, right? Although I don't know if I want to sit here and try to fill air while we watch that little bar fill a bunch of times, right? But again, I think we can observe that it's doing better, right? So a little bit of a discussion to have right now. I kind of went over this very, very quickly. I presented a lot of this like it's pretty easy and obvious, and I think some of you might be sitting there terrified, right? Because some of you might be thinking, oh my God, does he think the thing that he just did is like a 10-minute project? No, I don't. The first time I did this, it took much, much longer than 10 minutes. Maybe I'm admitting to being stupid, but figuring out all of these little details, getting all of this stuff to work just so, the first time I figured out, oh, I need to kill the silent ones, I need to get the silence out of there, right? So the first time I was like, oh, okay, I really need to think about, like, how much time I'm talking about given the sample rate, and if the data I want is really capturable there, right? All of these were little moments that took me a while, right? And then I had to look up, how do you do X, Y, Z, or how to figure it out myself, right? And sometimes, even if the solution ends up being simple, arriving at it is not. So what I'm basically saying is, do not think that the fact that I went over this in 5 minutes means that I think you could write this in 5 minutes. I am not that stupid, okay? Okay. All right, so it looks like our loss is going up again, right? Our loss is trending up-ish, although not ferociously, right? So we might still have some tinkering to do, right? Our network might still not do a particularly good job, and we might still have some tinkering to do to really get this where we want it to be, right? But again, that's sort of a little bit of the name of the game here. You make an educated guess, you try it, you go, you try it again, and there are some long stretches of waiting for your network to run to see what you got, right? I think that's most of what there is to say about this. And again, the crux of it, the simplest bit, is just right here, right? That is the soundfile.read method that just hands you a NumPy array of your audio data. And you can process it the way that I did, right? This is not the smartest audio processing function you could write. For all I know, TensorFlow has a smarter one built in. It probably does. I'm sure if you look up online, you'll be able to find people who have written much more about much smarter ways to do this. But this works, right? This is a minimal, fairly comprehensible thing that works, I think. All right, so next unit is going to be the pillow, and that'll be it.